Hello? Yeah, great. Hey, everybody. Let me move this. All right. Clap once if you could hear me. Twice if you could hear me. Hey, everybody. We have to move fast, per usual. So today we're going to do everything purely slides, or iPad at least. So what today is going to look like is we're going to talk about secret sharing, and then switch to error correcting codes. And error correcting codes, I have some real polished slides for that. That's what I did my job talk on to get this job. So we'll switch to those in a moment. But we're going to do secret sharing first. So yeah, just a warm-up problem. Let's say you and a friend open up a joint emergency bank account. But neither of you trust yourselves to not just use it whenever you want, to not impulse buy. So you want to, there's a 6-digit PIN to get into the account, but you don't want either of you to have it. You want to find a way so that you can split the PIN so that you can only recover the PIN if you both come together and share your secrets together. So yeah, let's just say for a second that this is secret S. And I don't know, let's just pick some number, 873291. The question is, how can I split that secret into 2 shares so that we can't, yeah?
One person gets the first 2 digits, the second gets the last 3 digits, and assuming that you, assuming not one cheated and looked at the whole thing, you don't know the PIN.
Yeah, so this is a perfect way where we can just split 2 things. It's like 2 parts of like a locket. You kind of have to put them together, and then you have the thing that you want to use. 2 parts of a key. So this absolutely works. If you have S1 but don't know S2, you don't know S2. You can't do the complete PIN. On the other hand, you know a lot about the PIN. You either know the first half or the second half. That means instead of having the amount of security of having to guess over 6 digits, now you only have to guess 3. Like you could brute force that maybe. So like, is there something better that we can do other than splitting down the half, which reveals a whole bunch of the PIN, or half of the PIN? And this isn't necessarily obvious, but yeah, let's give it a go. So let's say n is equal to 1,000,000. Oops. 1,000,000 because 6 digits. 6 digits go from all zeros to all nines. Let's wake this computer back up. So yeah, it goes from all zeros to all nines. So if we looked at what Zn is, the PIN is going to be some number in Zn, which starts at the all zeros string and goes to 9999999. I cut that off a little bit bad. Oh no, it's not even, okay, there it goes. So our PIN will be one of those numbers, right? All zeros to the all nines string. So here's one thing we could do. Here's the scheme. You could choose random S1 in Zn, right? Just choose a random number in there. And then the other part is set S2 to be S minus S1. So now what do we have? We have 2 numbers, and for correctness, what we have is then S1 plus S2 is going to be S1 plus, we'll just plug it in, S minus S2, and that's going to be congruent to S mod n. And yeah, that should be mod n as well. Okay, so now this is something that reveals no information, right? If you choose a random number S1, you don't know what the other person's number is. I don't know. It's, oh, maybe it's just not on me well enough. Yes, thank you. I'll clip it to something more sturdy here. Okay. Better? Okay. So, right. If all you have is S1, you have no idea what the PIN is. It's not like having the first half or the second half. It's, yeah, whether you have S1 or S2, the other number could be absolutely anything, right? So this completely breaks any sort of knowledge that you could gain. So this is a nice little concept, just a nice little warm-up. Let's look at something a little bit more tricky. Let's say you're now in a group of 5 friends, and you want a joint account, like a joint bank account, for a group vacation. And you want to split the accounts PIN so that choosing to use the account, choosing to go on a vacation, you need majority vote. That is, you need any 3 other 5 friends can combine their secrets to recover the PIN. Much trickier, right? So first off, if you just had S1, S2, what we're trying to do is create 5 secrets so that any 3 of them can combine to the original secret S. So kind of the tricky part here, well, if we forgot about all this, right? If all we cared about is a group of 5 friends and they all needed to come together, we could do the same thing as before, right? We could just choose random numbers in Zn for S1 through S4, and then just set 5 to be the thing you need to add to get all of them to be S. So like if you needed all 5 friends to come together to do this, you could just choose these randomly and everything would work through as before. The tricky part now is you want this threshold function where like if these 3 friends come together, their 3 secrets somehow can be combined to get the original secret S, or these 3 friends, S1 and S4 and S5, or these 3 friends. You know, you want any 3 to be able to come together and create a secret. Much harder. Like it's not obvious how you would do this, at least not with the way we've been doing. And if you look in the notes, this is commonly motivated as, you know, something where you want to make a majority decision. You want a threshold for enough people to agree on a thing before it can be unlocked. The first one you could almost think of as, you know, those movies where 2 people have a key and the keyholes are on the opposite side of the room and you need to like turn the key at the same time to open the vault. That's basically what this is. You want to split the keys so that you have to all turn them at the same time to actually open something. And in the notes, and this is often motivated as like nuclear codes. You don't want one person in charge of nuclear codes, so you have like, you need at least 5 of the 7 delegates to all agree that we want to open the nuclear codes at once to actually unlock them. Oh no, not again. I don't particularly want to think about nuclear armaments being in a small group of hands right now. So we're going to talk about a vacation fund. So we have a vacation fund. We have 3 people. We need 3 people, a majority rule, to unlock it. And how do we do this? And this isn't obvious if you haven't seen it, but once you see it, it's so clean. So the key thing we're using here is if we have 3 points of a function, one thing we saw last time is that uniquely gives us a degree 2 polynomial. So this is going to be what we're going to use here. 3 points give us a unique degree 2 polynomial. So here's going to be our scheme. And, you know, we have to get to error correcting code, so I'm not going to pull this out of you. I'm just going to tell you what it is. And what we're going to do is we're going to choose a random, choose a random degree 2 poly such that the constant term, f at 0, is the secret S. What does that look like? It's going to look like, you know, some degree 2 polynomial. There's going to be an A2 coefficient. There's going to be an A1 coefficient. And then there's going to be the constant term, which we're setting to be S. So the S is hidden as the constant term of some degree 2 polynomial. And what we're going to do then, the second part of the scheme, is to give out the secrets. One secret is going to be the evaluation of f at 1. The second secret is going to be the evaluation at f2, and so on until we get S5 equals the evaluation at 5. Oops, not enough parentheses there. Yeah, that's a little messy. Let me make that cleaner. And be careful not to get your 5s confused with S's. Sorry for that. So The point is, if we have 5 evaluation points of a polynomial, then if any 3 people come together, they can recreate that entire polynomial. That's the key of polynomials. All it takes is 3 points to define a degree 2 polynomial. Polynomials are kind of this magic thing. They have a bunch of evaluation points, but they don't take that many points to actually nail down exactly what the polynomial is. Yeah? I'm saying you define one polynomial. So the question is, do you define a polynomial with different sets of 3 unique points? I'm saying you define one polynomial, and then you look at the evaluation points of that polynomial. So let's just take a quick look at a picture here. So let's say we have a parabola. Let's say the secret here. Here's the secret. It's S. Oh no. So this isn't showing up here. Maybe there's just some lag. Okay, there we go. Right, so we have some parabola, right? This is our parabola right here. Poorly drawn parabola. But what its secret is where it crosses its y-intercept. Where does it cross the y-axis? And we have all these points here. 1, 2, 3, 4, 5. And those are all evaluation points on that parabola. So the key is, how do we do this? We just choose random coefficients, and that defines a degree 2 polynomial. And the thing is, if 3 friends get together, let's say these 3 friends get together, 3 points is enough to make a parabola through Lagrange interpolation. This is what we showed last time. If you have 3 points, you can interpolate those 3 points and recover the entire parabola, which gives you S. If it was a different set of 3 people, those sets of 3 people, that's still 3 points on a polynomial. You can recover your entire parabola and thus your secret S. This is the key to secret sharing, is you just get shares of a polynomial. And the structure of polynomials, this is why, again, math is useful in computer science, is because math gives you structure. And if you just have 3 points of a parabola, that's all you need to fully reconstruct it. So, and on the other side, if we had just 2 points here, let's say we have 2 points, that's not enough information to fully recover, because what if S was here? Then the parabola might look like this, and we wouldn't know the better. If these 2 people got together, they wouldn't know what S is, because what if S was up here? That would be a different parabola. They can never really know with just 2 points what the parabola looks like. It could be any other parabola that passes through those 2 points, and all of those can pass through a different S. So any questions on this? We're going to look at a little bit more complex example, but this is the foundation of secret sharing. Yeah? Yeah, great question. There needs to be someone that does that, or you write a computer program that generates a pin, generates a secret, creates a polynomial that passes through it, gives out all the points, and then throws away the secret and kind of trashes all of its work. Yeah, you can't have someone do that, otherwise they have the secret themselves. Yeah. Great question. So, you're saying if we had 6 people, but still we just wanted a threshold of 3? So, yeah, great question. How do we know the threshold? So we want to set the threshold. We want to say at least this many people need to share their secrets to unlock it. So what did we base how big of our polynomial is? That wasn't based on 5 at all. That was based on the number of people that need to come together. So if there was 7 people, but all you cared about is not majority, but only 3 people need to get together to unlock it, you'd still use a degree 2 polynomial. You would just have to give out more shares. You'd give out 7 shares of the polynomial with the expectation that 3 people need to come together to unlock it. Right. because 3 points make a parabola, and that fully defines the curve, which gives you the y-intercept. Yeah? No, 3 isn't the majority of 7. So you get to decide the threshold. You might want to say for 7, if we care about majority, then we'd say the threshold's 4. And if the threshold's 4, then how big of a polynomial would we need? Yep, we'd need degree 3 if we had a threshold of 4. Because 4 points uniquely define a cubic polynomial, a degree 3 polynomial, which again gives us the y-intercept. Yeah? Yeah, so what would we actually give? We would actually give these. Like the secret S1 is the evaluation point. It says, okay, you get the valuation point of 1, and here's the value, it's f of 1. So that'd be some number, right? They'd say, well, it's evaluated to, I don't know, let's say this is 7. So one person's secret would be 1, 7. You know? And each person gets a different point there. And to combine them, you could use Lagrange interpolation. Yeah? Yes, so the question was, does this work the same irregardless of the number of people? Like if you just have a threshold of 3, would this always be the same? And the answer is yes. You can scale this up to as many people. If all you care about is a threshold of 3, it'll always be a degree 2 polynomial. The only thing you need to worry about is, we haven't really been talking about this, but we want to be doing this over a Galois field. Just so we have finiteness, we're not dealing with approximations, we're not doing with all the ugliness of polynomials. But we want to work over a nice finite field, Galois field, of some p prime. We'll talk about this in just a moment, but yes, yes, you do, you want to make sure p is more than the number of people. Why? You just want enough evaluation points. If you don't have a large enough finite field, you don't have enough points to evaluate on your polynomial. Yeah?
Since we talked about kind of like once you have that polynomial, right, the points, the different secrets can be kind of arbitrary because they can be any points along the graph.
Yeah.
Now, does that apply to the secret itself, where you can make it any, like let's say in this case you make f at the intercept at 0, right? But can you make the secret at any other intercept?
Yes, so the question is, we put the secret at the y-intercept. Why didn't we put the secret here and then just give everyone else all these other points? You could. You absolutely could. There's nothing special about it being the y-intercept. That's just a simple way to do it. It's nice to make the constant coefficient s and then just have all the other points kind of lay where they are. But you absolutely could. So last question before we move on to error correcting codes. First off, this is called Shamir secret sharing. The first thing we looked at was also secret sharing, where you just kind of divide it up into 2 things that you add together. This polynomial idea is Shamir secret sharing. That's the same S as in RSA. I forgot to mention RSA is an acronym for names. Ron Rivest, Adi Shamir, and Len Adelman. Shamir is the S from RSA, and also secret sharing here. So here's a new example. You're designing a communal wiki and you have 6 moderators and 30 contributors, and you want to be able to do a hard reset to like a previous archive point of the wiki if things go terribly, terribly wrong. But you don't want anyone to just hard reset your wiki. That'd be a bummer. You want that to be kind of like a group communal decision. So now we want to design a scheme so that 4 moderators can recover S, or 24 contributors can come together and share their secrets to recover S, or 3 moderators with 6 contributors. So this one's a bit more tricky, right? There's a bunch of different thresholds. Certainly if all 24 contributors come together, maybe they can share their secret and then share their secrets and unlock S, the pin that lets you do a hard reset. but you also trust the moderators quite a bit. They have a lot of knowledge, inside knowledge, and they have commitment in the sort. So you say only 4 moderators need to come together to make the secret. So this is less obvious how to do, but let's go through and see how to do it. And this is frozen again. There we go. So, yeah, let's just see how to do it. So, let's start with the simplest one. It's not clear what the simplest one is, but in retrospect it might be. If we have 24 contributors, what can we do from that? If we were thinking of it as just this problem, we can create a degree 23 polynomial. Those exist. It's a high degree, but that's fine. Just create a degree 23 polynomial f such that, like we had before, the constant term, that's supposed to be a0, is equal to the secret s. So what happens here? If this is the case, then everything works as before. There's 30 contributors, but 24 of them come together. They uniquely define a degree 23 polynomial, and you can recover s. So certainly, it's certainly the case that for this place, 24 points does give you a degree 23 polynomial. Now the question is, okay, what about this 4 moderators thing? How do we deal with 4 moderators coming together? Any thoughts on that? Yeah. We can give each moderator 6 keys. So each contributor only gets 1 key, but you could give each moderator 6 keys. So now if they come together, 6 times 4 is 24, and they can interpolate that degree 23 polynomial. So let's write this out. The scheme is this. Give each contributor, I'm just going to say conch, each contributor 1 distinct point of f, while on the other hand, we can give each moderator, I don't want to say mod because we are using moduli everywhere, so mod might be confusing, so let's say modder. Give each moderator 6 points of f. So now, if we look up here, 4 moderators come together with 6 points each. That's also 24 points, and we can get that same degree 23 polynomial. On the other hand, this just kind of works out because I wrote the problem. But if you have 3 moderators with 6 contributors, that's, well, let's see, 3 times 6 is 18, plus 6 contributors. 18 plus 6 is, in fact, 24 points, and that gives us 23. So, yeah. Yeah, it doesn't have to be 6 specific contributors. Yeah, so the point is, if you have enough shares of the polynomial, if you have enough points of the polynomial, it doesn't matter who you are, it doesn't matter which group comes together, so long as you end up getting 24 points of the polynomial together, you can interpolate them to get that degree 23 polynomial and thus find your secret that is the y-intercept. So no, it doesn't matter who comes together, so long as at the end of the day you have 24 points. Yeah?
Why can't we create like 3 completely separate polynomials? Like say 1 for each case.
Yeah, so there are other ways to do secret sharing. If you have different groups of people, instead of all having 1 polynomial and different amounts of shares, you can create different polynomials that kind of intersect at the secret. So that's a different way to do it. I forget if that's mentioned in the notes. I think the discussion section will go over that. But yes, that is another possibility. You can absolutely have multiple polynomials for the different groups of people. Yeah? That is trickier if you want to combine 2 groups. I believe there's ways to do it, but it is, it is trickier to combine two groups like we have here. Right here, we're combining two groups. We're having 3 moderators with 6 contributors, and that does, it does make having a single polynomial kind of a better fit for this design problem specifically. So this is basically all we want to say on secret sharing. There's one more thing, which is, well, let's look at this. We do want to make sure these are all distinct. So we have one, f of 1. We're going to have all these shares, right? Each one of these is a different share, dot, 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 all the way to 30, f of 30. All of these, let me open that up. All of these are going to be the 30 different contributors. And then we keep going from there. We have 31, f of 31, and we just kind of keep getting all these points all the way to 36, f of 36. And this right here will be, there we go. This will be moderator 1, right? The moderator gets 6 shares, and then you keep going, right? You go on to 37, all the way up to, what's the next multiple of 6? 42? 42. Right, this should have been f of 37 here. And this is f of 42. And that's moderator 2. And then so on for all the rest of the moderators. So, yeah.
Is the difficulty of this sort of finding the polynomial contingent on how big the Galois field is? So if you have a really big P in the Galois field, would it be much more difficult to predict than when it was smaller?
So the question is the secret. Is the secret easier to predict if you have a smaller Galois field? And the answer is no. It's kind of information theoretically protected if you have any less than the amount of threshold you have. If you have 23 points, the problem is if you have 23 points, you could think that the secret could be each one of the other P's, and that would give you a completely different polynomial. So it's information theoretically ambiguous which the secret is. The only thing we do need to be careful here is that P is bigger than the secret. Otherwise, the secret itself wraps and you lose information about the secret. And it also needs to be bigger than the 30 contributors plus the 6 shares that each of the 6 moderators gets. So it has to be bigger than 66 because we need 66 evaluation points. We need to create 66 shares, so we need at least that many evaluation points. That's all we need for the size of P, a prime bigger than that. Yeah?
If there are 24 contributors, why do we have 30 points? Why are there 6 extra points for the...
Right, so we're just defining what the threshold is. So this is just how many people are working on the wiki. There's 6 moderators and 30 contributors. And the design problem is, okay, if we have 24 contributors agreeing we need to do a hard reset, that's enough of the 30 contributors that we cross the threshold and are able to. Okay. Any questions on secret sharing? Because now we're going to move on to error correcting codes. This is more conceptual. We didn't do too much math. Most of the math we did last time learning about polynomials. This is just kind of this really cool conceptual thing. Yeah? Sorry, can you say that one more time?
Because we just had to add those 24 points, so can we just have like 2 moderators and 12 contributors, or like 1 moderator and 8 contributors?
Oh, yes. So this is true, yes. So like the maths differently so that you do end up having different ratios of people that can end up unlocking. The real thing is if you get 24 points together, you can unlock it always. So if you didn't want that, you would need a lot more cleverness, maybe different polynomials, maybe different, right. What we set up satisfies these conditions, but there may be other groups of people that could get together, like some number of moderators with some number of contributors that can unlock it once they get 24 points. Yeah?
So then if they don't share like a common factor, like the number of moderators and contributors, like because they both share the factor of 4,
Uh-huh.
would you need to polynomials to like...
Yeah. So like the idea is that there's not too many points you need of a polynomial to fully recover it. And you can just kind of leverage that idea as much as you want. Sometimes, like, yes, if you, this worked out really nicely because I set up the problem nicely. If the specs you have for designing such a secret sharing thing were more tricky, you might need to be more clever with how you're thinking about polynomials and how you divide up shares or make multiple polynomials or what have you. Yeah? Right. So the question is, why do we need a field? And, well, we don't. This works over the reals. Everything we said works over the reals. It's just computers don't work the nicest over the reals, especially if you're doing approximations in the sort. It's real nice to just have some finite numbers. A finite field is nice because it's finite, but all the math we expect to work over the reals also works over that field. That's why we work over these Galois fields, because multiplication works out nicely. That's why we always have a prime p. Mm-hmm. Yeah? Right. So if p equals 6, just all of your properties start breaking apart. You don't have, if you're working over z6, all of your things start breaking apart. We saw this yesterday or Tuesday, where x minus 1 times x minus 2, and we're trying to solve for that. We know x equals 1 works. We know x equals 2 works, but also x equals 4 works. Because this will be, if you plug x in, it'll be 3 times 2, which is equal to 6, which is congruent to 0, mod 6, which is a problem. So this breaks, for example, property 1, which says a polynomial can only have the degree many roots. This has more than the degree many roots. So you just start breaking all your properties, and your multiplication doesn't work. Yeah? Oh, the question's, if you have 2 points, can you figure out the third point? I'm not sure. The math may make it so that there's not even a unique S secret, even if you have 3 points. I'm not positive. Your math really starts to break down if you're not working over a field. The property 1 breaks. We've used property 1 to show property 2, that there's a unique polynomial. That's how we use that. So, like, if you don't have that, you start losing a lot. So we are not going to go into the details of like how exactly it breaks, but the reason we're working over a field is because all of our math, all of our multiplication specifically, works out great, and all of our algebra works like we expect it to. Yeah? You mentioned a little while ago that this is secure from the information perspective. Mm-hmm. You could guess every possible secret in P. Yeah, but there's no way to check that you got the right one unless you have more. So the question is, like, can you just guess every possible secret in P until you have the right one? I mean, to the degree that you could guess it and then plug it in and see if you hard reset the wiki. But now you're back at trying to guess the pin from scratch. And that's back where you started. Like, you could always try to brute force the pin. Okay, so we're going to move on to, so we're going to move fast through this. This was my job talk. It's extremely polished. I do want you to be careful, though. It's so polished it could slip right into your brain and right out. You know, I put a lot of thought into these slides, and that's thoughts you're not having. So, right. So, like, I do want to be careful. It will be a great reference material. It's recorded, so you can just kind of keep going back and rewatching it over and over. But it might seem really sleek, but do be careful because yeah, we're going to be moving real fast, and you might sit down with the homework and be like, wait, what did I learn again? It felt like it made so much sense. So I try to build in parts for you to think, but we're going to be moving fast. Yeah? We won't be going over Hamming codes. We'll be going over what's called Reed-Solomon codes. Mm-hmm. Yeah. I can post the notes from the, oh yeah, the notes from the iPad, the one I just did for secret sharing. Yeah, I can post that. I can post these slides as well, but they have a lot of animation, so they don't read that well. But the recording absolutely will be. Okay. So the job talk, we don't need to know a lot of this. I'm just giving the context for, CS70. You know what a polynomial is. You know what modular arithmetic is. I call it FP there. We call it ZP or GFP, but that's a finite field of prime order. And this is a prereq for the course, solving systems of linear equations. We have a sense of how to do that. So that's just the, the background that we have coming in. This warm-up we're going to kind of skip to because we've already done it. We did this yesterday. We've done this already. We can play the part. How many points uniquely define a line? 2. Yeah, great. Two. If I draw 2 points, can you see the line already? Yep, it's right there. So this is everything we did yesterday. A line, famously, a degree 1 polynomial. We can ask the same thing about a degree 2.
3.
Yep, thank you. So if you have 3 points, you can uniquely interpolate those with a parabola. Great. And then, we know this degree 3 is 4. It gets a bit more squiggly. And then we did this yesterday, right? So, like, if we go all the way to degree 100, that's... 101. Yep. And, it gets real squiggly there. And then, of course, this is what we proved, which is d plus 1 points uniquely define a degree d polynomial. We proved this with Lagrange interpolation. We're actually going to see how to interpolate d plus 1 points a different way today. But Lagrange interpolation is what we did. So, degree d polynomials, we know 2 things about them. We had 2 properties that we wrote down last time. This was one of them, right? So this, we'll call this 1, and there's a second one. This is flipped from the notes. Property 1 is property 2 and vice versa. But this property we've seen. D plus 1 points uniquely define a degree d polynomial. That's how we used for secret sharing just a moment ago, too. And a corollary of this is that if you have 2 polynomials, p and q, that agree on d plus 1 points, then the 2 polynomials have to be the same. Right? And this is just saying it doesn't take too many points to nail down a polynomial. Another way to say that is if 2 polynomials agree on too many points, they have to agree on all the points. Right? 2 polynomials can't disagree on that many points without agreeing everywhere, or can't agree on too many points without agreeing everywhere. And then, okay, snap judgment. If I asked you to solve both of these in your head, who'd rather solve the top one? Who'd rather solve the bottom one? Yep. Right there, yeah, you can see the zeros right there. There's 5 and 6. Yep. And this is a little bit of a trick question. They're actually the same polynomial. One's just factored version of the other. And this is kind of a philosophical point, but we've done this a lot in this class now. But most of math is just starting with something that's true and then just rewriting it and rewriting it and rewriting it until it fits in our head. It's so hard to fit things in our head, and most of the time we just try to start with some definition that we know is true until we can write it into something that fits into our head. But they're saying the same thing. So this is a theme we'll see as the talk goes on. But yeah, and from this motivation, this is what we talked about last time too. Any non-zero degree d polynomial has at most d roots. The idea is factoring. You can factor into its d roots, and those are a degree d polynomial factors into its d roots, and those are all of its roots. And just a quick note is, why is this true? Well, why do we know 5 or 6 have to be the zeros? Well, because we know if a times b is equal to 0, that must mean that a is equal to 0 or b is equal to 0. That's not always true. If you're not in a field, that's not true. That's what we saw last time. That's why we get, like, if you're mod 6, like was just said, you can get another root in there. It's a big problem. 2 times 3 is equal to 0 mod 6, and neither of those are 0. But if you're in a field, this works out. Okay. So we're going to come back to that point. But yeah, we're going to leave that on the left side, and in the middle, that's going to be our bread and butter slide. We're going to come back to it over and over again. But for now, let's talk about what error correcting codes are. So let's say I have a message, 3, 0, and 5. And let's say I'm going to I want to send, and let's say there's metadata too, 0, 1, and 2, that we know what the indices are. And what I'm going to do is I want to pass this message, 305, to Professor Hug over there. So I write 3 on a piece of paper, crumble it up, throw it to Professor Hug, write 0 on a piece of paper, crumble it up, throw it to Professor Hug, same with 5, and throw it to Professor Hug. But as I do that, each time I try to throw it to Professor Hug, let's say Aya likes to stand up and knock one out of the air. Just can't help it. You know, it's just spike it out of the air, get that ish out of here, just spike it. So that's called an erasure error, where instead of getting all 3, 0, and 5 across, one of them just gets knocked out of the air. So what if we have this one erasure error? So the idea is, can we encode it? Can we do something so that even if one gets knocked out of the air, the whole message gets across? And what's the very, very simplest thing we can do here? Just the simplest bare bones thing of how to get more message across so that even if one gets knocked out of the air, the whole thing gets across. Any thoughts? Yeah.
Can you send it again?
Yeah, we can repeat it. Instead of just sending it once, we can repeat it a whole bunch of times. So now if one gets knocked out of the air, well, look, it's still there. And they have indices, so you can always recover. So, you know, like, if something gets dropped in, like, this TCP IP network, the way that works is the receiver says, hey, I think I missed something. Can you retransmit it? We're trying to not do that. We're avoiding that. Maybe retransmission cost is really high. Maybe we're Voyager way out in space and sending information to Earth, and we don't want to get information to Earth, and Earth says, hey, I missed a packet there. Can you resend it? So you want to send it all at once, or maybe someone's offline later. You want to send it all at once, all in one fell swoop. So, okay. The point is, this is called a repetition code. You can repeat it a bunch of times. So even if something gets knocked out, we're good. So now let's look at, it might be a little hard to see there, k equals 3 erasure errors. What happens if we have 3 erasure errors? Does this still work? Well, I mean, it kind of looks like it does. Look, if I knock all 3 of those out, the message still gets through. So why doesn't what we did right here work for 3 erasure errors? Yeah. Yeah. So, you know, if all 3 of these get knocked out, not big of a problem. But what if all the zeros get knocked out? What if those are the ones being knocked out of the air? Well, what can I do? The solution is pretty simple. If I know there's going to be 3 erasure errors, that is, I know that Aya gets tuckered out after doing it 3 times. I know there's only going to be at most 3 erasures. I can just send it a 4th time, right there. Right. So now we have, we can send it 4 times to handle 3 errors. In general, if we have k errors, we can repeat it k plus 1 times. Right. Simple. Just repeat it k plus 1 times, so k errors you'll always have the whole message recoverable. So this is called a repetition code with k erasure errors. And it takes an n symbol message, and it creates an encoding that is n times k plus 1 symbols. Why? Because if you have k errors, you're repeating it k plus 1 times, right? That's all. We're just repeating it k plus 1 times. So what's wrong with the erasure code? It sure does seem to work. Well, let's take a look at an example. Let's say one symbol is a byte, and let's say the fraction of erasure errors that are going to happen, or the number of erasure errors that's going to happen, is a fraction of n. Let's say it's 1/3 of your message. Well, let's look, let's see. Let's say we're dealing with a small photo. I'm trying to send a small photo. It's 3 megabytes. If we remember what a megabyte is, it's 1 million bytes, so this is 3 million bytes. A megabyte is 1 million bytes, depending on who you ask. So 3 megabytes is 3 million bytes. And now let's do the erasure error to it. So we know k is 1/3. So yeah, the code word is going to be n times k plus 1, so let's plug everything in. We have 3 million bytes, and then 1/3 of n, because k is 1/3 of n. So let's, those 3's cancel, fine. And what we're left with is 3 times 10 to the 12. Those 10 to the 6's multiply. This is 3 terabytes. That's bad. we started with a small photo, and now we're ending with a large SSD. We start with actually quite a small photo. 3 megabytes is a small photo, and what we're ending with is a large hard drive. The repetition code works, but is untenable. We have to do better than that. Okay. So what we're going to talk about is the Reed-Solomon code for erasure errors. These are two people, Reed and Solomon. A lot of these things have names from papers. Reed and Solomon were the authors. So let's say we have this message 3, 0, and 5 now. And what we want to do is, instead of repetition, we want to encode some type of redundancy. And this is going to be where we're going to kind of jump tacks again and just kind of find something clever, more clever than repetition code. And what gives us cleverness is structure. Of course, this is on polynomials, so we're going to be thinking about polynomials. Let's think of the message as evaluation points. That is, these are the indices. These are the evaluation points. So 0, at index 0, the message should be 3. At index 1, the message should be 0. At index 2, the message should be 5. And, well, you know, if we have 3 points, we can plot them out. And what do we know about 3 points? We know that a degree 2 polynomial, or we know from our bread and butter slide that d plus 1 points uniquely define a degree d polynomial. So coming back here, we know these 3 points will uniquely define a degree 2 polynomial. So if we have those 3 points, we could just pass a parabola through them, uniquely defined by those 3 points. And now let's look at this encoding. The encoding is, well, let's just keep the message as was, but realize what this message is now. This message isn't just 3, 0, and 5. It's evaluations of a polynomial. That each of these points, each of these symbols is one evaluation point of a polynomial. So now we can extend it. So for index 3, what do we put in there? We could just put the evaluation of that polynomial at index 3. So if this gets erased, no biggie. Their whole message is still right there. No problem at all. But what if instead of that one getting erased, that got erased? Yeah?
We still have 3 points. We can still find the parabola. We can still find that point.
Exactly. All we need is 3 points. We could still completely recover the polynomial. Why? Because of our bread and butter slide, right? We know that d plus 1 points uniquely define a degree d polynomial. So 3 points will give us the polynomial. So even though we got rid of one of those, these are still 3 points of the polynomial. We can fully recover it, plug 1 in, and find out what should have been there. All right. So let's make this a little bit more concrete, though. We've been talking abstractly. Let's find out what that polynomial actually is. Let's look at that example. So let's put numbers up there and actually plot it out. We have 0, 3, 1, 0, and 2, 5. Those are those actually plotted out. And let's say we're going to work mod 7. Just a small prime. There's nothing important about that number except that it's prime. So let's just do mod 7. This will stop looking like a parabola because it wraps the modulus. But everything's going to work out fine because we're working over a Galois field. We can use all of our intuitions because polynomials behave the same because we're working over a field. It'll just look all wonky. So we have this discrete, kind of broken up parabola, fine. And now we want to see how we can actually solve for this equation P, solve for the polynomial. Now we're going to interpolate those 3 points in a different way than Lagrange interpolation. Quite simple, actually, or it's quite elegant. So let's see, what do we know about that polynomial? Well, we know that when we plug 0 in, we get 3. We know that when we plug 1 in, we get 0. And we know when we plug 2 in, we get 5. Those are the 3 things we know about it. And if we simplify what we just wrote there, we get a system of linear equations. Which is pretty wild because, like, polynomials aren't linear. Right? Polynomials aren't linear, but the nonlinear parts are what we plug in constants into. Right? So the x squared, that's no longer a variable. We're plugging constants into there, so now all we have left are the coefficients. So what we have is a system of linear equations, and we can solve systems of linear equations. So if we solve for A0, A1, and A2, don't forget to do mod 7. We're working over a modulus. If we're working over that, we won't solve that system of linear equations. I'll just tell you. A0 is equal to 3. It tells right there, but then you can start plugging it in from there. But you solve for those coefficients, and that tells us what the polynomial is. That's just going to be 4x squared plus 3. Right? That's just the coefficients plugged in. So now we know what the polynomial is. Right. So now that we know what the polynomial is, we can just keep evaluating it if we want. Right? So if we want more points, we can just keep evaluating on more points. So P3, I'll tell you, that's just 4. If you plug 3 into 4x squared plus 3 mod 7, you do all your modular arithmetic. We know how to do that now. We get 4. So now what happens if, and we can just keep doing that. We can do it for evaluation point 4 now. How many errors can this handle? 2. This can handle 2 errors. Why? Because any 3 points gives us the whole polynomial. It doesn't matter if these 2 points are lost. If we have 2 errors, if these 2 points are lost, we still have 3 points, and that fully defines a degree 2 polynomial. It doesn't matter which 2 points are lost anywhere here, so long as we have 3 points left, we can fully define the polynomial. If we go one further, show me on your fingers how many errors can we handle here? 3, exactly. Because again, all we need is 3 points. There's 6 points here. So long as we have 3 points left over, we can handle that. In general, if we have k errors, we can have n plus k. We can handle k errors with n plus k points of degree n minus 1 polynomial. Why? Because if you knock off k of those points, you still have n points left, and that uniquely defines a degree n minus 1 polynomial. Okay, so a key point of this, endpoints completely define a degree n minus 1 polynomial. A key point of this, though, is that you can think of polynomials as data structures with extra structure. So it might be a little cut off for you there. It says polys are data structures with structure. So we're using polynomials as data structures themselves that have a bunch of redundancy built in. Yeah?
Can I see again how we got in mod 7?
Right. So we didn't really talk about mod 7. I just chose a prime.
Just any prime.
Yeah, any prime. If you want more evaluation points, you need a bigger prime. Otherwise, you run out of evaluation points. But it's not so important what the prime is, so long as it's big enough to handle all the evaluation points you want. Yeah?
How do we know what k is?
That's part of, you have to set it. You have to say, I want to handle this many errors. So it's part of a protocol. It's kind of the specs you set up. Yeah?
When we were originally doing this, when we originally said for P3,
Mm-hmm.
was that to say that what we sent would be P of 3, or it would be the evaluation of P of 3?
Yeah, right. So P of 3 is the evaluation of 3 on that polynomial. So really what the code word is it's just it's right here. It's P of 0, P of 1, P of 2, P of 3, P of 4, P of 5.
Because what I mean is that you
Mhm.
have 3 points to be able to derive the polynomial.
Yes.
So if you only have 2 and then some arbitrary P of 3, you wouldn't be able to do that.
So you need 3 points to derive the polynomial. Can you repeat your question one time?
You need 3 points to get some f of x where you can
Yeah.
use f of x to get everything else.
Mm-hmm. Exactly.
But if you have, like we said, for 3, 5, and some P of 3 without knowing what P of x the equation is, so you
Yeah.
wouldn't be able to do that.
So you said 3, 5, and P of 3?
Yeah, back when we had that, as
Right.
without knowing
Great question. Right. So we're not just being given 3, 0, and 4. We're given the points 0, 3, 2, 5, and 3, 4. We know the indices as well. The indices say if you plug 0 in, you get 3. If you plug 2 in, you get 5. If you plug 3 in, you get 4. So we have all of those evaluation points. And if we have 1, 2, 3 points, that's enough to fully recover the parabola and tells us what all of these points will be. Because we know the polynomial will be 4x squared plus 3.
Okay, my confusion is initially were we saying that the third point was 3 comma 4, or was it 3 comma p of 3 without knowing what p is?
Oh, yeah, so we don't know what p is. What we will know is what's being given would be exactly, it's 3 comma p of 3. In this case, p of 3 is equal to 4. So that is one of the values given. So if you have this point, you have this point, and you have this point, that's 3 points of the polynomial. And you can recover what p is because 3 points uniquely define what that quadratic polynomial is, what that parabola is. Okay. We can talk about this after class. Very happy to. There's a question back here. Yeah. The modulus, again, you can think of all of this over the reals. We introduced the modulus for finiteness because we're working on computers. We want discrete finiteness. We don't want to approximate anything. It's for niceness. Okay. So, yeah, the point there being polynomials are data structures with structure. Polynomials are very powerful. We only talked about 2 properties, and those 2 properties give us so much. They give us this sort of redundancy where a polynomial is evaluated on so many points, but it only takes a few points to recover the whole thing. That's why they're great for error-correcting codes, because you only need a few points to recover a lot. Great. So let's see what we did here, because we talked about the repetition code. Now we're talking about the Reed-Solomon code. So M is n symbols. And now the code word, when we're using the Reed-Solomon code, is n plus k symbols. We can handle k errors by just adding k more evaluations of a polynomial. So why is this better than repetition codes? Well, let's see. Back to the same exact example. Say 1 symbol is 1 byte. K is a third of n. That's the number of errors we're handling. And M is a small photo, 3 megabytes. So same exact setup. Last time we blew up to a hard drive, 3 terabytes. How are we going to blow up here? Well, let's see. The code word is n plus k. So n is 3 times 10 to the 6, 3 million bytes, plus a third of that. That's plus is the big distinction here. It used to be times, now it's plus. Those 3's cancel, and what do we end up with? About 4 million bytes. That's 4 megabytes. That's another small photo. That's fine. You know, blowing up from a small photo to a terabyte was awful, but going from a small photo to a small photo, that's a fine error-correcting code. Right. So now we have, 3 megabytes to 4 megabytes. Right. So, okay, that's the Reed-Solomon code with erasure codes. We're going fast. Now we're going to talk about the Reed-Solomon code for general errors. That's a nice concept. It warmed us up a bit, but we're going to be talking about the Reed-Solomon code for a different type of error other than erasure errors. So let's look at what we did before. We have a code word that we made. This is our code word. It's a bunch of evaluations of a polynomial, but that's not what's received. What's received goes through a noisy channel and gets 3 general errors. What are general errors? Well, it's almost like erasure errors. You get 3 points getting knocked out of the sky, but instead of just being knocked out of the sky, they're corrupted. They're replaced. So, well, I don't see the problem too much here because, look, here's 3 points that are uncorrupted. All we need are 3 points to uniquely define the parabola and find everything. So why can't we do that here? What makes this harder? Yeah. We don't know which points are the correct points. There are imposters amongst the correct points, right? Like it might be these 3, but we don't know that. Maybe we think it's these 3. And we can't know which ones to interpolate to find the correct polynomial. This almost seems like it might be impossible to do. You know, it's like, well, how could you do that? If you have that much corruption, then like, how do you actually recover it? So we're going to see how. It's quite surprising. But general errors seem harder, and we want to know if we can even do it in the first place. Okay. So what can we do? We start, and again, we have our code word, and this is the received code word, which is just some corruption of what we actually do. So before we say how to do it, let's give some context. This is more in the context of streams of data. Instead of like a network passing system where we drop packets, that's kind of what we were talking about last time, almost like a network packing where packets are dropped. Instead, we're going to be talking about streams of data. So like, what's an example of this? Like deep space communication, again, Voyager out in the sky, like deep in space, trying to communicate back to us. What it's doing is it's beaming electromagnetic signals at us so that we can get a message. But there's a lot of electromagnetic signals in space. You know, there's solar flares, there's all these things that can just corrupt the data coming at us. Also, there's these things that called compact discs. We used to put music on them. DVDs are what Netflix used to send you in the mail to watch a movie when you wanted to watch one. Those used to get smudged, they got scratched. You could get corrupted data. Your CD reader, your DVD reader would read incorrect data. It's not just gone, it's corrupted. And also something more relevant, QR codes. If you go to like your menuless restaurant now, you have QR codes, and those are error corrected too. Those get scuffed all the time. And also, like, sometimes you see a little picture in a QR code, like a little logo. Why can they do that and it's still readable? Because of Reed-Solomon codes. Reed-Solomon codes are used on QR codes, so you could put a little picture there. That's corrupting the data, but you still have enough data to actually recover the whole, all the data that the QR code encodes. All right. So let's see how to actually do this. Let's look at some small examples. Let's say n equals 2 and k equals 1. So n equals 2 is the number of message symbols we're sending. So in this case, it's a line, and k equals 1 is one error. So if I show you these 4 points, can you tell which one is the error? Right. There's the error, and there's the line. Now, what if we just had these 3 points? Can you tell which one is the error here? Yeah. Because, you know, maybe that's the line, and that's the error. Or maybe that's the line, and that one's the error. Or maybe that one's the line, and that's the error. It's ambiguous. We don't know. We don't have enough information to know. So there was something special about this line passing through 3 points. So let's talk about, you know, what is special? What's special about passing through 3 points? I'll give you a hint. 3 is equal to 2 plus 1. And k is equal to 1. We only have one error. So if we pass through 3 points, and even if we thought one of those might have been an error, we still know that there are 2 correct points. And 2 correct points is enough to know that we have the correct line, because 2 points define the line. So if we have 2 points that we know are on the line, we know we have the correct line. All right. So let's just remember, we used 4 points here. 3 points wasn't enough, but 4 points was enough to uniquely determine what the rest of the code word was, even if one of the points was corrupted. Okay, let's look at a little bit bigger example. N equals 3 and k equals 2. So now we're looking at a parabola, and we're allowing 2 errors to happen. So can you see the errors here? More importantly, can you see the parabola? If you see the parabola, you see the errors. Right? So the point is, if you pass through 5 points, if a parabola passes through 5 points, that is enough to know you have the correct parabola. Why? What's special about passing through 5 points? Well, I'll give you a hint. 5 is equal to 3 plus 2. And we only are dealing with 2 errors. So if we pass through 5 points, if a parabola passes through 5 points that we received, and we know only 2 are incorrect, even if we thought 2 of those might have been incorrect, what we do know is that there's 3 correct points on that parabola. And 3 correct points uniquely defines the parabola. So we know we must have had the correct parabola. Okay, so let's look at this more generally. We saw n equals 2 and k equals 1, and we needed a 4-symbol code word for that. We saw n equals 3 and k equals 2. We need a 7-symbol code word for that, because we need 5 points to pass through that, to pass 5 points through a parabola to pass through 5 points. So make a guess. How many symbols, or how big of a code word do you need to handle n and k, handle k errors? Just make a guess in your head. We're going to have n plus 2 k's. So that works for those two. We're going to see why it works in general. So if we have an n plus 2 k symbol code word that handles k errors, That's going to imply some things. It's going to imply two things, in fact. Let's go ahead and see what they are. But first, before we do that, this n plus 2k, let's just rewrite it as n plus k plus k. Small difference, but it's going to be helpful for us. N plus k plus k. Okay, so what does this imply? First off, if you chop off k of those, we know there's only k errors. There's at most k general errors. That means if we chop off k of those, we know that n plus k of the received points are uncorrupted. Right? If we have n plus 2k code words and only k are corrupted, we know that n plus k of the received points must be uncorrupted. And we're going to, one way to say that, or one corollary to that, is that there's a degree n minus 1 polynomial passing through those n plus k points. That's what the Reed-Solomon code is. It's a degree n minus 1 polynomial. And if it passes through n plus k points, well, we know if we received n plus k uncorrupted points, that means that the Reed-Solomon code, the polynomial, passed through n plus k of those points. So we know that there is a degree n minus 1 polynomial passing through those n plus k points. That's just something we know from using n plus 2k points. And two, this one is going to be even less obvious. So let's walk through it. It's that if we have a degree n minus 1 polynomial that passes through n plus k points, property 1 says 1 exists. But if we have a degree n minus 1 polynomial that passes through n plus k points, it must be the code word polynomial. It must have been the original polynomial p. That's not obvious. So this one's less obvious. Let's prove it. All right. So proof. How do we prove this? Proof. Well, let's just do it like implications proof. Let's assume the antecedent. Say q of x is a degree n minus 1 polynomial, and it passes through n plus k points. We're just assuming the antecedent here. So what we know is that there's only k errors. And if there's only k errors, this is kind of what we were doing before. If there's only k errors, that even if we thought k of those points were imposters, even if we thought k of those points were incorrect, what we still have is n points that are correct. So those must pass through that n minus 1 polynomial. So let's break this up a little bit more. So right, if we know we only have k errors, we can chop off those k points. And if we go back right up there, n plus k, this is why we did n plus 2k, so we could chop off k twice. Because now we've chopped off k for property 1, and we're able to say something, and now we're able to chop off k again to argue something for property 2. So this is why we have n plus 2k. We can kind of strip it off twice, and what we're left with is n correct points. N correct points must pass through the polynomial p because n points uniquely define a degree n minus 1 polynomial. We're going fast, but this is rewatchable. So only k errors, that means that, only k errors means that there's at least n points that are uncorrupted. And that means that q, so it might be cut off there, I'm going to read it to you. Q passes through n points of p. P was the code word, and q passes through n points of p because we know n points are uncorrupted. And what that means, again, this is cut off a little bit, that means q of x must be equal to p of x. Why? Because of our bread and butter slide here, right? This is what that corollary says. If two polynomials agree too much, they have to agree everywhere. So if q agrees with p on n points, that's too many points. P and q must be the same polynomial. It's uniquely defined by n points. All right. And that proves it. There's that little symbol there. Hopefully you can see it. And this will all show up probably better on the recording because you can see the whole thing if the bottom's chopped off for you there. Okay. So let's see how to actually do this now. Right. What does this tell us? It tells us, let's go back one. What does it tell us? It tells us that if we have an n plus 2k symbol, code word, that there is some degree n minus 1 polynomial that passes through n plus k points. That's property 1. And property 2 says that polynomial must be the original polynomial p. So this gives us a way to decode. So if we have n plus 2k symbol code word for k errors, here's going to be how we decode. We can find a degree n minus 1 polynomial that passes through n plus k points. And that's it. It must be the correct polynomial by property 1 and 2. Property 1 says it exists. Property 2 says it's the correct polynomial. So we need to find some polynomial that passes through n minus 1 points and n plus k points and is degree n minus 1. So this gives us a brute force algorithm for solving this. It's 3 steps. One is guess the k errors. Just guess them. Interpolate the remaining n plus k points for to get a polynomial q. And if the degree of q is less than or equal to n minus 1, we know q and p must be the same. We found it. Otherwise, we need to go back to step 1. Well, yeah, in this case, we're done. Otherwise, and this is cut off a little bit, it says else go to step 1. So what's the problem with this? This does work. But the problem with this is we're going to go to step 1 often. This bottom part, it says go to step 1. We're going to have to repeat this a lot. We're just guessing where the k errors are. And we'll see this on Tuesday. We'll be talking about how to count things. This is combinatorial notation. N plus 2 k points, and you're choosing k to see if k are the errors. We haven't talked about what that symbol means yet, but it's a way to count. And I'll tell you, it's going to be approximately that. Like, that's how many choices we have for k errors. And if we go back to k being like a third of n again, then that's going to be on the order of n to the n. That's so bad. That's kind of the worst. Like, it's real bad, n to the n. So this is untenable. It works. It sure does work. We can find the polynomial this way, but not in our lifetimes. So let's find a better way. Yeah, so can we find errors faster? That's what it says down there. Can we find the errors faster? And what we're going to do is what's called the Berlekamp-Welch decoder. Okay. So this is going to be a pretty cool trick. Also, we're going to be going fast through it, so you're going to have to rewatch it. So we have a message. There's n symbols in it. And we're going to interpolate it with a polynomial p of x to get a degree n minus 1 polynomial to get our code word. And that's going to be n plus 2k symbols. We're going to evaluate it on n plus 2k points. We're just walking through the setup of what we're doing again. We have a message. We interpolate it with a polynomial. We get a big old code word. And then it goes through some noisy channel, and we get a received code word, which has k errors in it. K of those are corrupted. That's the setup of this problem. And what we want to do is we want to use the Berlekamp-Welch decoder to get back to the original message m. This is the setup of the problem. And what Berlekamp-Welch decoder will do, it's quite surprising, is it will efficiently correct up to k general errors for an n plus 2k Reed-Solomon code. It'll identify where the errors occurred, and it'll tell you when r is too corrupted to recover m. That's quite a lot to do. It seems like you might have to do all these special cases of like, well, if this, then that. It's going to be quite elegant and surprising, and we're going to go through it now fast. All right. So the trick here is this, again, incredible thing where math gives us structure. So we want to start with natural language and go to polynomial land. Can we write natural language in algebra? Because algebra we can work with. So let's start with a simple example. Let's say in natural language, r, the received code word at index x was uncorrupted. That is, r at index x was uncorrupted. So that is, like, let's say there's some index x up here. There might be a lot of errors, but not at x. X is one of the places that's uncorrupted. It's one of the ones that's not scribbled out. Right? So that's what we're saying in natural language. That is, there's some x over here, and it is maintained there. So how do we say that in polynomial land? Well, how we might want to say that, well, what we remember is what is at index x here. It's the evaluation of the polynomial p of x. So to say this in polynomial land is to say that the polynomial evaluated on x is r of x. R of x didn't change from what that polynomial says it should be. this is now an algebraic statement. We're going to rewrite it. This is just subtracting on both sides, but it'll be helpful for us to write it that way. But now we've taken this natural language statement and written it as an algebra statement. Okay, so that's a little example. Let's look at something a little trickier. Now we're going to say, in natural language, either r of x was uncorrupted, or there was an error at index x. It's a simple thing to say in natural language. It's almost a tautology. Yeah, so it's almost a tautology. How do we write that as an algebra statement in polynomial land? Specifically, how do we write that or? How do we write an or as an algebraic statement? And here we're going back to our bread and butter slide, but not for the two properties we're used to using over here. We see a big old or here, and that's where if we know a times b is equal to 0, we know a equals 0 or b equals 0. That's where we're going to use to be able to encode or as a polynomial, as algebra, even though it's natural language. All right, so how do we do this? All right, so p of x minus r of x equals 0. We know that means r of x was uncorrupted. So we're good on that. Where does e of x come from? Well, we're going to see what that means in a moment. This just kind of gets pulled out of nowhere. We kind of wish for it, and we'll see what happens. Sometimes you have a eureka moment. Sometimes we just have to, again, like the other slide, sometimes we just have to follow our pencil and just rewrite something over and over again until it fits into our heads. So that's what we're going to do here. Again, this E kind of pops out of nowhere, but who's willing to suspend disbelief for a moment about what E is? Okay, yeah, we'll just kind of put that on this back shelf for now, and then we'll get to what it is. So this happens, but if two things multiply to 0, we know that either that's equal to 0 or E of x is equal to 0. That's E of x. So we know now we have an or, and it almost matches up. So let's kind of look at it one more time. Let's say that E is a degree k polynomial. Why? Because it'd be nice if it was. Let's do with that and follow our pencil and see what happens. So if E is a degree k polynomial, what do we know? Well, if P of x is not equal to R of x, then E of x must be equal to 0. That's just saying this one is false, so this one must be true. That's how ORs work. So if P of x is not equal to R of x, then E of x is equal to 0. And if it's a degree k polynomial, then we know that the roots of E are errors. That's what it says for P of x to not equal to R of x. E are the errors. And what do we know? Any non-zero degree D polynomial has at most D roots. So if we know that, we know what the roots look like. It's going to be E1 all the way through EK. Let's call those the errors. And that happens if and only if, and this is going to be a little hard to see, E of x is equal to x minus E1 times x minus E2 all the way to x minus EK. That's the form it has. And if we translate this back to natural language, what this says is there was an index there was an error at index these. Okay, so let's kind of write what we've done. We're just about out of time, so I'm going to go quick here. E of x is going to be of this form. Every degree D polynomial has at most D roots, or K roots in this case, so those are going to be them. That's called the error locator polynomial. It's this magic thing that you kind of wish for, and then poof, there it is. It's as good as you would want it to be, and it exists. So, yeah, we're going to be a little bit out of time here. I do have this all recorded because this was my job talk. So there's 5 minutes left at most, but I think we have too much to go through, so I'm just going to post this online. There's going to be 5 minutes you didn't get. Just watch the video online, and that'll be it for today. Whew. Fast.
So pretty.
Thanks.
Wow, it felt like I was watching a YouTube video.